So I put up a folder on Canvas that has some practice exams for the upcoming exam, as well as the formula sheet. I also wanted to mention that one of the, I think the last recording, like the last 30 seconds, my voice is very robotic in it. And when I view it on my computer, it doesn't look like that happened. So I don't know if it was coming across that way on Zoom, but if that ever happens, let me know. I can't remember if it was this section or not, but sometimes it's just a matter of me resetting the mic. Also, if you're watching it on YouTube and you see that, let me know about that as well, because I like I said, when I view the file on my computer, it looks okay. So maybe just kind of splicing it and re-uploading it, I could probably fix that audio issue. So if that ever happens, please let me know about those. This is not what I wanted. This is from the last class. So let's go here. And let's go down to this first question. And then we'll go. Okay. So I want to set something up, and then we're going to look at this hypothesis testing example tuition file, okay? So what we've been talking about with hypothesis testing is we've got, let's say, a sample mean, the distribution of our sample means, and we've assumed that they're centered around some value, right? Let's for a second assume that what we have assumed to be true, right, ends up like after the fact, we were able to somehow get our hands on the population data and we say it is in fact the true value. Okay? If that's the case, whatever alpha we set, right, so you can kind of think about it as whatever alpha we set, anytime we see a sample mean in this range, the area to the left of that, right, so let's say I see this is my sample mean, and I said the area to the left, sorry. The area to the right of that represents my p-value, right? So anytime I see a sample mean that's kind of past this cutoff value of alpha, I'm going to have a p-value that's less than alpha, and I'm going to reject this assumed true mean. Well, now, if we can look back after the fact and figure out, well, no, that assumed true mean was, in fact, exactly the true mean. For every one of these sample means over here, I would have been rejecting when I shouldn't have been. And so that's why we say whatever we set alpha at, that's what we know our type 1 error is going to be. When we reject, even though we shouldn't have been, because that ended up being the true population mean. So that was kind of our type 1 error, was this idea of alpha in this tail, right? So I'm going to draw something a little bit different. So we've got kind of alpha in this tail here, which represented our type 1 error. What if instead we have this assumed true mean, but in fact, we, after the fact, can look at the population data and figure out, well, no, actually, the true mean was over here, okay? Well, now, if we think about this scenario, every value for the sample mean that we saw here, we actually didn't have a p-value that was less than alpha, so we failed to reject all these values, even though we in fact should have been, because the true population mean was all the way over here. So you can kind of think about if we were trying to identify our type 2 errors, it would look something like that. Right? Now I'm not going to there's nothing like this will be on the exam in terms of type 2 errors. I'm just trying to give a discussion really today and next week will be me presenting things in a slightly different way, kind of revisiting ideas that we had talked about in the past, type 1, type 2 errors, and then showing you some more example, hypothesis testing examples. So we've got this idea of a type 1 and type 2 error. What if we go back to trying to understand that type 1 error a little bit more? All right. So I have this Excel file that's on Canvas, which was hypothesis or HT example tuition, hypothesis testing example tuition. Okay. So let me zoom in here. I've got all these different universities and what their tuition was in 2012. In fact, I'm pretty sure, let's see if we can find it here. Well, let me search. Yeah, Ball State's on the list, right? Oh, I didn't want to select it. But there we go. There's Ball State, right? There we go. So here's all my data now. This is population data. I have every university in 2012 here. So I can calculate the true population mean, right, using that average function, the true population variance, var.p, of that tuition variable. With that true mean and that true variance, let's say, for a second, I assume, like this is kind of a weird scenario because I do have the population data, but I'm going to assume that the true mean is exactly this value. Right? I'm cheating because I was able to see the population data, but like, I'm going to assume that that's what it is. So then what I did, I kind of used this column to help me build this very first sample, which was 50 random universities. It kind of used these random numbers to pull out random universities into this sample. Okay? So I've got 50 random universities. It's putting in their tuition amount. One school, Jesus. 49,000, right? So we've got these random, 50 random schools. Well, that's my sample. I could calculate a sample mean by just taking the average of that first sample. Once I had that, I found the sample variance here, but I didn't need to because someone, say, told me what that population variance was. I have that assumed true population mean, which we said we were cheating. We're going to assume it's exactly equal to the population mean. So there I just calculated my test statistic. I took my sample mean, I subtracted the true population mean, I then divided by the square root of that population variance over this count is just counting up my sample. So it's going to be my sample size, which for this sample is 50. Okay. I then use that test statistic. I know that because I'm using the population variance, it comes from the standard normal distribution. So I'll use that norm.s.dist. Now here, it didn't matter if I had a negative or a positive test statistic. The reason why I kind of set that up in Excel is if we think about what's going on there, if from my sample, because I'm going to do this for 1,000 different samples. So if for the sample I found a negative test statistic, I want the area to the left of it, right? And then multiply it by 2 if I'm treating it as though it's a two-tailed test. If I had found the positive test statistic, I would have wanted to find the area to the right of it and then multiply it by 2 to get my p-value. So if I just take the absolute value, since this is a symmetric distribution, this would fold on top of itself, and I could always kind of treat it as a right-tailed test. So that's what I did. That's what I'm doing here, treating it as a right-tailed test after I take the absolute value of that test statistic that's right above this. Then I treat it as a two-tailed test, so I'll multiply it by 2. Okay. So I did that for this first sample. I then did it for another random 50 schools, and I took 1,000 different samples of size 50, right? So here's all my samples. Here's their sample mean, their test statistic, their p-value. And then that last row, what I did was say, well, look, I'm going to figure out if I can reject or not. If that p-value I calculate is less than what's in cell T2, well, if we're using the p-value approach, it should be, I'm comparing the p-value to alpha. So here alpha is 0.1. So if the p-value is less than alpha, put a 1 because I should be rejecting, a 0 if not, right? Because I'd fail to reject. I then did that for every single one of these 1,000 samples. Down here, I then added up all those rejection decisions. So really by summing up this row, I'm adding up the number of times that I was rejecting, right? Out of those 1,000 different samples, how many times was I rejecting? 106 times. Or you could think about it as a proportion. We could take that, divide it by the total number of samples I took, which was 1,000. And notice every time I click on a cell and hit enter, it randomly generates new numbers. So I'm getting things that are slightly different. But notice they all kind of are really close to 0.1. Sometimes slightly above it, sometimes slightly below it. But they all center around that alpha that I chose. Well, why? because if I rejected here, because we assumed the true mean, whoops, not that cell, sorry. Because we assumed the true mean was, in fact, the true mean, right? Every time I made a rejection decision, I shouldn't have been. I was making a type 1 error. Well, alpha is our type 1 error, so whatever I choose alpha to be, that's the kind of proportion of type 1 errors I'll be making. Now, it's not exactly 0.1 here because I only have 1,000 samples to truly get, I need an infinite number of samples, which isn't realistic, right? It's not possible to get an infinite number of samples. But if I, maybe copy this over and did it for like 2,000, we'd get values that are even more close to that, barely above that 0.1. If I change my alpha, so let's change it to 0.01. Now notice the proportion of type 1 errors I'm making center up right around kind of 0.01. Sometimes slightly above it, sometimes slightly below it, okay? So that's kind of the idea behind what we're trying to do, or kind of taking a step back and just thinking about hypothesis testing in a slightly different way, okay? Any questions on that? Are you good with that? I know in my earlier section I had some really good questions that came up, so I'll try to kind of hit some of those as I'm walking through things, but it's always good to kind of ask questions, even if it's just via the chat. All right, so we have this idea of type 1, type 2 errors. The next thing I want to do is try to work through a problem, okay? So this first one, right? Consider the following hypothesis test, right? So we've got that the assumed true mean is 9,200 or 9,200. The alternative hypothesis is that the true population mean is anything other than that value, right? So right away we know we have a two-tailed test, right? So if we have this two-tailed test, we then find a sample mean. We'll use this problem 1 to start out with. We take a sample mean of 9,200, or find a sample mean of 9,290 from a sample of size 105. We're given a known population standard deviation, and we want to do this hypothesis test at the 10% significance level. So the general setup of what we have is my sample means should be normally distributed around whatever that assumed true population mean is. I find sample mean that's slightly higher than that, right? So can I reject this as the true value, right? Could I say, based off the sample evidence I found, I'm going to reject this as my assumed, I'm going to say that 9,200 or 9,200 can't be the true population mean, right? Well, I can do two approaches, right? I can do the p-value approach or I can do the critical value approach. Okay? So the first one is going to be, let's try to think about what the p-value approach would look like. So the p-value is essentially the probability I saw sample evidence that goes against the null as far away as I did or anything even further away. Now the problem is if we have a two-tailed test, which is what we had here, seeing 9,290, it would have been equally as likely for me to see something that far away from the assumed true mean, but below it, right? And that would go against the null. So you can think about this would be what, 90, 110? So really, the probability I saw something as far away from the assumed true mean as I did with my sample evidence, or even further that goes against the null, would be everything here, but also everything here. So I can find this area, but then to get my p-value, I need to remember whatever that area is, I have to multiply it by 2. Okay? Because I have an equally sized tail on the other side. Now, how can I do this? Well, I need to turn it into a standard normal distribution and turn my sample mean into a z-statistic or a test statistic, right? Then I can find the area to the right here, multiply by 2, because for a two-tailed test, I kind of two tails here. So how do I turn this value into my test statistic? Well, we had this equation. Let me see where I'm at. I got enough room over here. Where my z value is equal to the assumed true mean minus the, no, sorry, I said that backwards. I don't like the way I'm doing this. So, where can I write this where it's going to be easier to see? So I'm going to get rid of this for right now. So I'll take the sample mean that I found minus the assumed true mean, and then divide that by the square root of, I think it was 620, was our population standard deviation. Now the problem is, we actually want in that equation, here was our denominator, right? In fact, we just want to think about what's up here, right? We had something like that. So if I only have the standard deviation of 620, I have to make sure that I also square it and then divide by my sample size, which I think was 105 in the problem. Okay. So we can enter that into our calculator. I don't think I grabbed my calculator. So what you could do, and this is how I actually work through these things in my office when I'm kind of setting examples up for exams or anything like that. Get rid of this since I kind of did that earlier. So what I wanted was that 9,290 minus 9,200 divided by the square root of 620 squared divided by that sample size of 105. Right? So I'm just using Excel to be my calculator there. Okay? You could have entered that into your calculator and that'd be fine. Oh. Where did you get the 920? Oh, sorry if I saw this late. We're just working through this problem one, right? These are like several different problems we could run through that would just have different numbers. I'm going to just go through number one and number two today to kind of show you something useful, okay? But it just gives us some numbers that we can kind of play around with. Does that answer your question? Okay, so we found 1.4, what was it? To the second decimal, 1.49. So found our z statistic or our test statistic of 1.49. Now I can use my standard normal table, look this value up, but it's going to give me the area to the left. I want this area in the upper right tail, so I'll have to subtract it from 1. So I go to my table, I look up, oh gosh, come on. There we go. I look up 1.49. So the second decimal, 0.9 is the last column, 1.49, 0.9319. So 0.9319 is the area to the left there. I'm going to subtract that from 1. You get what? 0.0681. But that's not my p-value because that's just the area in the right tail. For a two-tail test, I have a left tail as well. I'll multiply it by 2. Yeah. You get about 0.1362. Okay. So this is my p-value. Right. Now I can start to think about my rejection decisions. Okay. So I'm just going to transfer some things over. So we found that p-value of 0.1362. Okay. And sorry, I probably should have asked if everyone had that down that's on the Zoom, but if not, you can kind of go back and look at it later to kind of complete that example. But we were dealing with that p-value. I wanted to make a point about our rejection decision. So we only reject if our p-value is less than alpha. So one way that you could probably set this up, write down your p-values and think about the 3 different alphas that we typically check against. Okay. Here is my p-value less than 0.1. No, so I would fail to reject. Is it less than 0.05? No, so I fail to reject. Is it less than 0.01? No, so I failed to reject there as well. So here we have an example where the sample evidence we found was far enough away from the assumed true value that we actually, sorry, that wasn't far enough away from the assumed true value such that we can't reject it at any level, okay? Now, what about, you know, I can't reject this with what, 90, 95, or 99% confidence? But what if I wanted to like reject it with 85% confidence? Yeah, my alpha would be 0.15 and I just barely could, right? So we don't want to get too caught up in like, you know, just hitting these benchmarks, because being able to say something with 85% confidence isn't exactly, you know, the worst thing in the world, right? It's still a pretty strong level of confidence, okay? Okay. So the next thing that we can think about, if instead of using this p-value approach, right, which we failed to reject at every single level, okay, I could actually use my critical value approach. So I'll leave this down here for now. So if I want critical values, we can think about if I'm dealing with a right-tailed test, those critical values should be coming from the right side of my distribution. Okay? So I want the z-value, or the critical value, that gives me alpha in this right tail. So let's do that first alpha, excuse me, 0.1, right? Well, if I go to the table to try to find this, and I look up 0.1, what's going to happen? I'm not going to find the correct critical value, because if I look up 0.1, remember the table always looks at the area to the left, so it's actually going to give me that same value, but negative, right? Which is okay. If I just want to look up alpha, that's the, kind of, as the area in the left tail, and I remember I have a right tail test, I could just look up that 0.1 and remember that it's going to be positive. So if I simply look up that area in the tail of 0.1, looks like I'm in between these two values, negative 1.28 and negative 1.29. So 1.29 or negative 1.29, I'll remember it's a right tail test. So it has to be positive. So 1.29. Okay. Now, I could have also thought about this as the area I want to the right of this value is 0.1. What's the area to the left? Just 1 minus that, or 0.9. So I could have also went to that table, looked up an area of 0.9 in between these two, 1.28 and 1.29, take the higher of 2, 1.29. Sure enough, same value we found if we just looked up alpha and remembered it's a right-tailed test, so the critical value has to be positive. Okay? So here's our critical value. Our rejection region is going to be anything to the right of that for a right-tailed test. The only other thing we have to do for the critical value approach is now, where does the test statistic, does it fall in that rejection region or does it not? If I remember right, we had that test statistic was, wait, did I say it was 1.49? What am I not doing right here? Oh, you let me get away with something because I wasn't thinking about this correctly. What did I forget to do here? So what was my original problem? Two-tailed test. Right. So I didn't just want alpha in this tail, right?
Yeah, you want to divide that point.
Exactly. I had to divide this by 2, right? So 0.05. So instead of looking up 0.1 or 0.9, I had to look up 0.05. So, or I could have looked up what, 0.95, because the alpha I want in this tail is there. I'd have 0.05 in the other tail as well, because for a two-tailed test, I should have pairs of critical values, right? Forgot about the original problem here. So now when I go and look up 0.05 in between these two, so negative 1.64, negative 1.65. So we'll take negative 1.65. For a two-tailed test, I have 2 critical values, so there they are, right? And then here's my rejection region on my other tail. Okay, now I can plot my test statistic, right? So my test statistic was what? 1.49. So where does that fall? Right? 1.49, not quite in my rejection region, right? Just barely outside of it. Okay? So both kind of approaches lead us to being, failing to reject. I didn't do the other two critical values, but we could look them up. But if I want to do a critical value for not an alpha of 0.1, but 0.05, well, that is a smaller area in the tail. So I'm going to have to look at a critical value that's even larger. Well, if it gets even larger, for sure my test statistic won't be in that rejection region, right? If I fail to reject with 90% confidence, I'm going to be failing to reject with 90, 95, and 99 as well. Okay? So I failed to reject at every level, although I'm not too far away from rejecting at that 10% significance level, and that's kind of what my p-value let me know as well. Okay. Any questions on that before we keep moving here? Anyone on Zoom needs me to kind of slow down? I want to erase that again. Okay. Before we go, we'll go to the next one. So we're going to think about, we're using all these same numbers, but instead, we're going to use this example, right? So we have the same sample mean. Everything else stays the same, but let's assume we found a slightly higher sample size. Or sorry, we use a higher sample size. I shouldn't say slightly. We used a higher sample size. But we found the same sample mean. We have the same hypothesis test, right? What's going to happen if that's the case? So we'll walk through kind of piece by piece. So if that's the case, in problem one, so to speak, here's my distribution. It was centered around 9,200. But if I remember, the standard deviation of my sample means is the square root of the population variance over my sample size, okay? So if I take a higher sample size, what's going to happen to my distribution for that second problem when I had a higher sample size, right? Well, if the sample size goes up, what happens to the standard deviation of my distribution of sample means?
It's going to be smaller.
Yep, because my denominator is getting larger, so that would kind of decrease this. If I have a smaller standard deviation or smaller variance, my distribution of my sample means is going to be more peaked, right? So that values around that assumed true mean should be way more likely for me to see, if it in fact is the true mean. So you can kind of notice, if I think about the sample evidence I found, right, same sample mean, before, unless I know it's a two-tailed test, but just for the sake of kind of showing you this, I'm just going to deal with the right tail. Notice this whole area was my p-value when I had a small sample size. When I take a higher sample size, it drives the variance or standard deviation down, making a more peak distribution. Now, if I find that same value, notice the p-value is much, much smaller, right? The area kind of under that tail. So when I take a higher sample size, it leads to a lower variance, but it's also going to kind of decrease that p-value. Okay? So if you want to write these down in steps, right, you could almost write step one. If I have a larger sample size, step two, I'll have a smaller variance in my distribution of sample means. Step three would lead to kind of me having a lower p-value. But here's kind of a nice visual of why. Now, with all of this, we can also think about, well, why is that p-value smaller? It looks like it here. It's pretty easy to see. I'm going to get rid of this for a second and think about, well, how would I actually perform this hypothesis test? I would turn this into a test statistic, right? And then find kind of the p-value. Well, my test statistic equation was take the sample mean minus the assumed true mean divided by population variance over my sample size. Because remember, this denominator represented that standard deviation of my sample means. So if my sample size goes up, what happens to the standard deviation, well, this denominator actually gets smaller. But if the denominator, the entire denominator gets smaller, what happens to my test statistic? Well, if the denominator goes down, my test statistic actually gets higher, right? So if I think about before, I would have this as my p-value. When my test statistic gets higher, and the blue is kind of my new test statistic, now my p-value is a smaller area, right? So this is why, you know, taking things with a higher sample size, if I'm seeing a p-value that's smaller, will it be more or less likely that I can reject the null?
It will be more likely you can reject it, right?
So I
Or
only
fail to reject?
more likely I fail to reject, right?
Yeah.
Because if I have a small p-value, a smaller p-value, it's more likely that my p-value would be less than alpha,
Okay.
right? So when I take a higher sample size, it increases my test statistic because, think about it this way. If I see the same sample mean, when I turn this into a test statistic, it's still a z value, it's a z statistic. So it's telling me the number of standard deviations away from the assumed true value. Well, if I take a higher sample size, if it drives down my standard deviation, now if I'm 100 or I'm 90 away, well, maybe now it's like instead of 2 standard deviations, maybe now I'm 6 standard deviations away, right? So my test statistic is higher, which means it was less likely that I saw the sample evidence I did if this was the assumed true value, which that's the definition of the p-value. So if I have a smaller p-value, it's just more likely it's going to be below that threshold alpha we set. So I'll be kind of, I know you can't quite see this, but I'll say it so if you're taking this, but more likely to reject there. Does that make some sense?
So like increasing your sample size will give you a more accurate result? Or is that a different?
I'd rephrase it, but that's a good way of thinking about it. If I take a higher sample size, I'm going to be able to reject more values or kind of narrow down the values that could potentially be the true population mean. Yeah. Yeah.
And so that it causes less type 1 errors, right?
I would be able to make statements at lower levels of alpha, which means making fewer type 1 errors. Exactly. Yeah.
Okay.
Yeah. Yeah, like if I went back to that Excel example, we could prove this to ourselves as well. If we like, instead of samples of size 50, I like copied the cells down so that I had samples of size 100. Then we would see like, I could use lower p-values to, yeah. No, it's a perfect way of thinking about it. Any questions on that online or? Let's see if we're good here. Okay. So, what are we on time here? Okay, pretty good. I wanted to do something else here as well, kind of give you a good visual of, it might seem kind of weird, but kind of connect this to what we were doing with confidence intervals. So if we had a two-tailed test, our confidence intervals and our hypothesis testing are going to kind of be similar. So let's think about, and we could actually kind of use the same example here. So let's say we've got this value of 9,200 and I see 9,290. Let's say, not use the example that we just did, but well, I guess we could say this. So what I could do is test that against this assumed true value. I failed to reject, right? So I could also almost think about it as here, this was a value I failed to reject. Well, if I failed to reject this, right? What if I tested for something that was even closer, like 9,250? Well, if I think about my kind of p-values here, I mean, it's the probability, it's the likeliness that I saw this as my sample mean if this was the assumed true mean. So the further I get away from that assumed true mean, kind of the smaller that p-value gets. So if I start choosing values that are closer to that, well, I'm definitely going to fail to reject for that one as well. So I could test all these values using my sample mean of 9,290, and I could even kind of start to test values up here at like 9350, and I'm maybe failing to reject all these, right? But at some point, if I say test against the value of 9,000, which is quite a bit further away, well, at some point there's going to be values where I say, well, look, if this was the assumed true mean, this is so unlikely for me to see, because if I assume the mean was over here, and I think about my p-value, I can barely even draw it. There's almost zero there, right? So I can start to test against these values, and I can reject those based off the sample evidence I found. Because if those were true, it'd be so unlikely for me to see this as my sample mean. So I can start to test against these values. Maybe I reject all these as well. I don't know. There's got to be some cutoff. I don't know what it is. I'm just going to kind of make it up just to kind of go through the example. Maybe it's like 9,170, and that's the last one that I failed to reject. Every other value past that, I was rejecting all these, right? And then there's some value over here that would be a cutoff where every value above it, I can reject these as well. Because now, if this was the true mean, same kind of idea, my p-value starts to get really small. Right? So think about kind of all these values in this range. I could do a hypothesis test for every single one of those values. 9,200, 9,201, 9,002, and I would be failing to reject for all of these. And then anything past these 2 points, I can start rejecting, right? Because it would start to be values that were far enough away from that sample mean that the probability I saw that as a sample mean would just be way too low, right? Well, what does this start to kind of look like? Well, if I can say that any value outside of these, I can reject as the true population mean, that's what I was doing with the confidence interval. I said only the values within the confidence interval could be possible values. Anything outside couldn't be. So it's really the same, really what we're doing with hypothesis testing is kind of the same idea as a confidence interval. We're just testing against one value. Well, why would I want to just test against one value when I could build a confidence interval and like tell you all the possible values, right? Well, we think about, we're going to have different p-values for each one of these hypothesis tests that we do, right? Because if I see this, remember, this was the sample mean that I found, this 9,290. Well, yeah, I failed to reject the values down here, but these values are way less likely to be my true population mean than values that I kind of right around that sample mean, right? I'm going to have much lower kind of p-values for the values out here than I am for hypothesis testing values that are right around that sample mean that I found. So it kind of gives us another dimension which we can compare which of these values are more or less likely, right? But it really is kind of related to confidence intervals. You can almost think about if I ran a hypothesis test for like every single one of these values, I could kind of build that confidence interval as well. All right, where are we at in time here? I don't know if there's anything else I want to say on this before we go. I have one more example that I want to work through. So I thought it was kind of relevant. So we just did kind of 1 and 2 there. I really wanted to do that to kind of talk about what happens if we do take a higher sample. Thinking about type 1, type 2 errors we started out with, and then kind of connecting hypothesis testing to confidence intervals. So a lot of this is, information isn't in the slides here, or it's really a lot of just hearing things said in a different way, presenting the material in a different way, revisiting some old material, connecting it to what we're doing now. I think hopefully we'll just kind of eventually, as we work through this all next week, doing kind of a similar thing, we'll be kind of prepared pretty well for the exam for these hypothesis testing problems. So let's say, I didn't want to do that. I wanted to go to here. So let's say I'm interested in predicting maybe the upcoming election, right? So this was today's. It looks like Biden's at like 49%, Trump's at 46%. So I'm going to use this sample evidence, and I think it says the sample size down here should be, 1,500 people, okay? So maybe I want to predict the upcoming election. I'm going to say, and third-party candidates kind of complicate this, but nonetheless, I'm going to say what I want to test for is whether or not the true proportion of people that will vote for Biden is less than 0.5, right? So I want to say, is it less than 0.5? I'll assume the opposite is true, which is that it's greater than or equal to 0.5. If the null hypothesis is true here, what does that mean?
That more than 50% of people voted for Biden.
Yeah, which means he wins, right?
Okay.
So if I can reject that, what I'm saying is that, well, the election's not a sure thing, right? And then, you know, we don't have the tools quite yet to be able to do a two population example. But at least here, if I fail to reject the null, what I'm saying is I fail to reject that Biden's going to get at least 50% of the votes or more, right? So we'll see if we can reject that or not, right? So we've got a left tail test. We've got this assumed true value of 0.5. I found a sample proportion of 0.49. So I could use a p-value approach, find the area to the left of that sample proportion, and then compare it to alpha. Right? Well, I'll get out of the way here in just a second. What we need to do is convert that into a z-statistic, right? So z-stat. And then find the area to the left, and that's our p-value. Okay? So the equation that we had for calculating that test statistic was take the sample proportion, subtract the assumed true proportion, divide by the assumed true proportion times 1 minus that assumed true proportion over our sample size, right? Where kind of the denominator here represented the standard deviation of our sample proportions. So once again, I'm going to use Excel as my calculator and just plug in 0.49 is the sample proportion, 0.5 was the assumed true proportion, and my sample size was 1,500. So we'll do this over here. So 0.49 minus that assumed true proportion of 0.5 divided by the square root of 0.5 times 1 minus 0.5 divided by that pretty large sample, right? 1,500 people. So I'm just using Excel to be my calculator here. Could have entered those values into my calculator. I get negative 0.77. So negative 0.77 is my z-statistic here. Negative 0.77. I can then go to the standard normal table, look that value up, and it'll give me the area I want. It's kind of the nice thing about a left-tailed test. Not quite as much work. So I go to the table, negative 0.77. So here's my second decimal. I scroll down. So negative 0.77. So the area to the left of it is 0.2206. So this area is 0.2206, which represents my p-value. So now I can start to think about what levels I can make my rejection decision at. Is 0.22 less than 0.1? No, which means it definitely won't be less than 0.05 or 0.01, right? So I failed to reject the null at every single level. So at our conventional levels, I failed to reject that Biden will receive 50% of the votes, 50% of the votes or more, right? Which, you know, if I'm trying to predict something, make some money, maybe I bet, you know, he's going to win the popular vote. Now, like I said, it complicates things a little bit here because we have two parties, in which case, like, you know, you could win with more than 0.49. But, you know, even at 0.5, we can't reject those as possible values. But I also want to point out, we could reject with like just under 80% confidence, right? Around 78% confidence, right, would give us like an alpha of about 0.22, right? So maybe you want to say 77% confidence. I could reject that. So with 77% confidence, I say I can reject 0.5 as one of the possible true proportions, population proportions, which means maybe we'll have a closer race, right? Maybe with 77% confidence, I could say the race might be pretty close here on Tuesday. Now, I do think if you wanted to, we could work through, I think that other value they had there was 0.6 was Trump. So we could do the same thing for Trump, but use that sample proportion of 0.46 because it had the same sample size. And we could see if we can actually reject that he's going to get more than 50% of the votes. So we'll change this to Trump's numbers. So 0.46. So -3, right? So if I look up kind of this test statistic of -3, the area to the left of that is 0.0013, right? So for Trump, this became like -3. That looks terrible. It's hard to write from the left side. Maybe I should just stay over here for right now. Which meant our p-value was pretty much close to 0, right? So if we only reject when the p-value is less than alpha, we can actually reject at the 1% significance level, or with 99% confidence, I can say that Trump's not going to get 50% of the votes or more, or a proportion of 0.5 or more. Which, you know, that rules out that he's going to like landslide win, but you know, when we're thinking about that, both those proportions will probably be below 0.5. You know, we can't make a clear-cut prediction. But yeah, I don't know. I thought it was kind of an interesting, you know, pretty relevant use of hypothesis testing we could do. And I used like one of the close polls. I'm sure if you kind of took some of the other ones, it'd be even, you know, be a little bit more. Yeah, exactly. Which one thing I did want to bring up, because I think it was interesting and it's relevant to what we've talked about in the past. I was looking at like, I don't want to. Okay, we're good. I think it's 538. So.
Oh yeah, those guys.
So they have a collection. Here we go. So they have like a collection of all these different polls that have been done, and a lot of them are kind of like. So this one is one they didn't. They're just like showing you that other people did it, and that was the one that we just looked at, and like I don't know, some of these are close. Like here, look right now, like Rasmussen. Over the last 2 days, right, has this like a neck and neck race. And this is just a popular vote, or this is like in North Carolina. So if we wanted to look at the whole popular vote, you know, we've got it kind of broken down by state. But one thing I thought was, you know, you start looking at this, when they have these like low grades, like these swayables, and then there's another one, Survey Monkey. All these are online surveys, right? So if you're not getting it from a place like some of these colleges will do one, or like these organizations, what do you think might be a problem if you're looking at those online surveys?
Who's put them out, and so
Who's put them out for sure, but even more so, who's going to be responding? I have a grandmother, and for the life of me, I know she could never figure out how to find a political poll online and vote in it, right? So it's going to be more young people, younger people tend to be more left-leaning. So when we look at these polling data, like the ones that are completely online, we got to be a little bit skeptical of, right? And I don't really, honestly, I don't care a ton about politics. I just think this is a really interesting example. Like when we look at results, we still have to remember those biases that might exist, right? Yeah, we can do this hypothesis testing, all this confidence interval stuff, but we got to, you know, if we're starting out with biased data, kind of all bets are off about how accurate our predictions will be. So I thought that was a relatively kind of interesting thing to think about. I don't know. I believe the Vegas odds way more than I believe a lot of these polls.
Yeah.
When money's on the line, you know, people try to do their best work. But that's kind of the last thing I wanted to mention. Next week, we'll just keep going through more examples. I'm going to put up an online quiz today that you should be able to get through really quick. It's just more opinions, so that I can. There's no correctness. It'll look like a survey, but you'll get 10 points for taking it. And it really is just like asking you about what difficulties you're having, giving you some options so that I know how I can, the direction I should take kind of lectures and things next week. Okay? All right. You know, any questions? You good? All right, everybody on Zoom, we're good. All right, have a good weekend. I'll see you guys on